I'd like to show you a pattern for prime numbers. So I guess we'll start by looking at our base numbers, 1 to 9. So there's a philosophy behind the numbers, how they all equal 9, and 9 is a big factor in how I found this pattern. So it's based on the Riemann hypothesis. Anyway, you've got 1 plus 8 equals 9, 7 plus 2 equal 9, 6 plus 3 equal 9, 4 plus 5 equal 9, and then you got 9 by itself. So back in Chaldean numerology, they still acknowledge 9, but they use numbers 1 to 8 because they knew that 9 was self-repetitious. It always comes back to itself. But that's another story that we'll get into at another time. So with those numbers, what I've done here, and you can see everything that I've done, this here that you're looking at is the Riemann hypothesis. It is the pattern for prime number distribution. So as you can see here, we've got all 9 numbers, and I've divided them into 3 portions. So 3, 6 and 9 are Tesla's numbers. Tesla's a famous bloke back in the early 1900s who had a lot of patents for different inventions. One of his famous quotes was, if you only knew the magnificence or the importance of the 3, 6 and 9, you would have a key to the universe. So we'll just keep that in mind for now. But as you can see here, we have 2 portions of numbers, and I've linked them through this number line down below. Now, 4 plus 5 equals 9. 1 plus 8 equals 9. 7 plus 2 equals 9. 3 plus 6 equal 9. And 9 equals 9. So that's the foundation for how I've distributed the prime numbers. So we'll start with the prime numbers, I suppose. We have 5, 7, 11, 13, 17, 19, 23, 29, and 31. These are the only primes that I'm going to look at here, because the pattern will obviously continue on, but this is all that we need to look at. So there's a thing called a digital root. A digital root and prime numbers, if you're not sure of what a prime number is, then there's no point in you watching this. But for those that are interested, we'll firstly look up what a prime number is versus a composite number. But to find a digital root, it goes back to Vedic and Sumerian Babylonian mathematics. We haven't been taught it at school, which is why this pattern has been left unsolved for so long. To find the digital root of 11, it's simply a matter of adding both digits together, 1 and 1. 1 plus 1 equals 2. To find the digital root of 13, 1 plus 3 equals 4. Now we want to find a number that resides between 1 and 9. So say you come to a number like 19. 1 plus 9 equals 10. So 10 isn't good enough in terms of it's still a double digit number and not a single digit number. So we repeat the process. What we do is add 1 plus 0. 1 plus 0 equals 1. So the digital root of 19 is 10. So just bear with me, guys. The whiteboard is working against me. I'll get this back up and be back online again. Okay, so now that we know what a digital root is, let's divide them into these number portions. Now, no prime number has a digital root of 3, 6 and 9, so keep that in mind. So this centre line here we'll mark as 3, 6 and 9. The top line, 417, we'll mark the top line, and 582 we'll mark the bottom line. So any prime number that falls on either the top or bottom line will be marked according to where the digital root positionings are. So let's start with 5. 5 will be down below. So 5 will be marked out. 7 is on the top line. We'll mark that out. 11 is a 2 because 1 plus 1 equals 2. So it will fall on the bottom line. 13 is a 4. 1 plus 3 equals 4. It will be on the top line. 17 will be an 8 because 1 plus 7 equals 8. So 17 will be on the bottom line. 19 is a 1 because 1 plus 9 equals 10, and then working with 10, 1 plus 0 equals 1. Therefore it's on the top line. 23 is a 5 because 2 plus 3 equals 5, so it will be on the bottom line. 29 will be a 2 because 2 plus 9 equals 11 and 1 plus 1 equals 2, so it will be on the bottom line. And 31 is beyond the number spectrum that I've marked out, so there's no need to include that. So now we have a different way of looking at prime numbers. Now all we do from here, and keep in mind that these dots that I've done in between, this will be a 1, a 2, a 3, a 4, a 5, a 6, 7, 8, 9, 10 and so forth. Oh, this is hectic. Sorry guys, bear with me. Okay, so all that we do is draw a line in between each one. So as we'll mark out 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 25, 26, 27, 28, 29 and 30. Seven to 5. Seven to 11. 7 to 17. 7 to 25. 'I stuffed that up. 13 to 5. 13 to 11. 13 to 17, 25. Mind you guys that this is obviously quite rough. I can show you better on the next side, but basically all of these weaves intersect at the 3, 6 and 9. 6, 9, 12, 15, 18, 21. I need to move that over more, but you get the picture of what I'm talking about. This shoots all the way along. So I'll show you up here what I mean. We have the top line here of the prime numbers that fill the 4, 1 and 7 category. Can't win, doesn't matter. So keep going along. Here are all the primes at the top. Now the primes at the bottom are for the bottom category of the 5, 8 and 2. 5, 2, 8, 5, 2, 5, 2, and they go along. Now if you have a look up here, just zoom back a little bit, just so I can show everyone.
Yeah, sure.
So you got 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39. They all go up by 3s all the way along. It's a pattern. So the numbers where they repeat from here, that would be 112, 113, 114, 115, 116, and so forth. So keep in mind that there's a 1 in front of these numbers because I've used 2 1 metre rulers. So obviously 100 centimetres to a ruler, and then it repeats itself. So you may question and say, hey, it's still not enough to show a pattern, and I'll agree with you. But if we look down below here, I've done it all in pen, and this black line here for 7 represents the black line that I've done here. The red line up here for 13 represents all of the numbers in red. So we'll go back to the black line again. We have 7 plus 6 plus 5. Then we have 7 plus 9 plus 11. If you just zoom out just a little bit. Yep.
Difficult to see them.
No, it's all good, brother. So we have here 7 plus 6 plus 5 equals 18, and 1 plus 8 equals 9. 7 plus 9 plus 2 equals 27 equals 9. Every single number adds to 9. Every single number in the red section equals 9. Every single number in the blue section equals 9. If I were to mark out all the ones in green, they will all equal 9. 9, 9, 9, 9. Every single one equals 9. So that is the pattern for the prime numbers. It really is as simple as that. The reason it hasn't been discovered yet is because mathematicians have this affinity with calling Vedic maths and things outside of the square, so to speak, as a woo-wah or hogswash. I've seen all the comments from different mathematicians, and they will not acknowledge Vedic maths. But you have the Holy Grail of mathematics right here, which is the Riemann hypothesis, and I have just shown it to you. So share this video and get any mathematician that you want to come and argue the point with me. You can't argue basic arithmetic of simple addition. So if you find that with every single string of numbers that I've done here, every single string adds to 9, and every intersecting weave falls on a 3, 6 or 9 all the way along from numbers 1 up to 200, then you can be pretty darn sure that this pattern is going to continue for infinite, because that is the law of probability. So I challenge anybody who has access or time to a supercomputer to put this in as an algorithm, and I will bet everything that I have on who I am that it is going to stay on the 9, and that this pattern will hold up for infinity. So there you have it, guys. That's the Riemann hypothesis. Thank you.